So thank you for the kind introduction. Yeah, as the name already implies, today we're talking about industrial robots. In industrial applications, especially when we want higher accuracy than the internal encoders of the robot can provide, one often uses an external tracking software such as this API Radeon system you see here. Now, there are different types of robot tracking technologies, and these can be categorized along two axes, mainly their measurement range as well as their accuracy range. And each implementation of a particular technology obviously covers a much smaller range than the total technology. But we see two problems in this area. First, for very, very high accuracy tasks, there is not really a technology, and each particular implementation of a technology has a very narrow range. That means that in practice, you have an industrial robot, you buy a laser tracker for that, costs 200,000 euros. You build a different cell, which might be a bit smaller, so the laser tracker needs to be closer, and the system doesn't work as well anymore. So we propose a different measurement technology, which we anticipate to have a much larger accuracy range, as well as a very large measurement range, and where each implementation can handle a variety of different ranges and accuracies. We do this using a modular system by having an active marker on the robot or a number of active markers on the robot and supervising these markers using a number of N cameras that are to be placed. Now, to get the required accuracy, we introduce an optical grating between the lens and the camera screen. This means that instead of directly observing the active marker, we instead observe the interference pattern. This allows us to also analyze the position of higher order maximas in these interference patterns to gain higher accuracies. Now, we already tested the system in a lab setup, but when we try to use it for the robots, there's a few problems we have to account for. So mainly, where do we actually place these cameras so that they all see the markers? Because remember, a robot is typically moving, and it's moving in a clouded cell. Secondly, the position of these cameras relative to each other has a strong influence on the accuracy of the system. You can imagine if both are parallel, looking the same direction, the XY plane has a high accuracy, but the Z plane has a low accuracy. And this is, of course, much more complex for N camera systems. So the idea was to build an algorithm that achieves both of these. So let's first talk about accuracy. What do cameras actually do? So to get the position of the markers, we do something which is called triangulation. That means that each camera is characterized by a particular projection P, which is made up of the internal camera parameters such as the focal length and other parts, as well as its position in the world. And each camera then converts basically the three-dimensional position of a marker X into its own position Y. Now, in some applications, you would have to also solve the correspondence problem, that is, which marker actually belongs to which image point. We don't have to do this. We use active markers, so they can be coded. So this means what we essentially do is we have a large system of linear equations where we try to find a world position X that explains all the image positions Y given our projection matrices. If we now try to analyze the accuracy of these systems, we can model the position error of the marker in the world frame as having two causes. For one, an error in the camera matrices, and for second, a measurement error in the image plane. This can be rewritten to have delta X or error in the position of the marker. And if we want to extract the magnitude of this error, which is what we're important, using submultiplication of matrix norms, we get the following result. Now, the right side is dependent on the initial errors and the world position, but the thing we want to optimize, of course, is the camera configuration, which is squarely in the left term here. And since they're multiplied together, minimizing this term minimizes the whole thing. So it turns out that you see this plus here is the Moore Penrose inverse of this matrix, that this term is equivalent to 1 over the smallest singular value of this matrix. That basically means if you want to have a camera system that triangulates particularly well, we want to maximize this smallest singular value. Now, modeling visibility, rather straightforward. We have two components here. We need to have a line of sight, which is either 1 or 0, and we need to be within the field of view, which can be measured by looking at the angle of the marker line of sight towards the optical axis. If this is smaller than our field of view, we're visible. If it's not, we're not visible. So first marker not visible, second marker visible, third marker not visible again due to a missing line of sight. And those two things now can be combined to a sort of objective function. So from the visibility, we get the right term here, which is basically integrated over the time of the robot task, because again, the robot moves, and as well over all the markers and all the cameras, which here the delta denoting the line of sight, either 1 or 0. Instead of just keeping alpha smaller than the field of view, we minimize it outright. Why? Two reasons. For one, it's simpler to optimize, and for a second, we actually also don't want these markers at the edge of our view, because there we have lens aberrations and other optical effects that might impact our system in practice. So we just try to have it as small as possible. And then from the left side, we have our smallest singular value, which we also want to maximize. Now, if you think about a 10 camera system now, each camera has 6 degrees of freedom. That means 60 degrees of freedom for a single system. Most iterative optimizers don't work that well for higher dimensions. Curse of dimensionality strikes again. So what we've developed is a sort of two-step approach, which we call double particle swarm optimization, where in the first step, we treat each camera as independent from all the others, and we neglect the field of view completely. That means we only optimize for line of sight in the first step, which leaves us a 3-dimensional system in terms of a 60-dimensional system. This gives us then a camera population who already have a line of sight. Then we randomly couple these cameras into camera positions, and now we optimize for the whole high-dimensional system. We can do this of course in a simulation of our real system. In this case, we chose this simulation of 2 robots working on a convex object where they cross in front of each other. You see the blue values here are the markers. And what you see here plotted is the 2 terms of the objective function respectively. And the blue histograms are the initial population of cameras, which were best guesses, and the red line is the final optimized solution. And we see the visibility is much improved. In the first cases, we have a visibility of almost 1, so everything is visible all of the time. It tends to go down a bit for the larger camera systems. That's because the system tries to prioritize between having the cameras be optimally triangulating and having maybe one of the 8 cameras not seeing the markers for, let's say, a second, which is why it goes down here. And at the same time, if we look at the singular value tends to go up in our optimized system, meaning that we indeed get larger accuracies of our system, or at least, you know, our upper bound of the accuracy increases, lower bound, I'm sorry. Now, next steps are we need to make a more robust experiment setup to have a complete error model of the system. The current problem here is that anybody who's tried to work with multi-camera calibration knows it's a bit tricky, and when you have to use active LED markers, it's even more trickier. So we're currently working on the calibration setup. So this is the current lab setup with, in this case, an example of 3 cameras and the active LEDs on our 2 robots. Now, that was my talk. I tried to be brief to leave a bit more room for questions. If you want to connect with me, there's my QR code. Otherwise, I'm happy to ask anything you want to know.